Okay, so we just talked about pure substances. Now we're going to talk about property tables in chapter 3. And then we're going to be doing some example problems. So the whole reason I showed you the states 1, 2, 3, and 4, and 5 of water going through those processes between 1 through 5 is because we need to start using, at this point we're going to be using tables in the back of the book to solve our problems. And so these tables are property tables, and in there you're going to see all the properties associated with a specific substance at a certain temperature, pressure, for example, and then there's properties associated with that substance at that pressure and temperature. So let's go ahead and have something here. Let me write some terminology here. So we have H here. This is represents a property called enthalpy, and it's a quantity of energy per unit mass that's associated with the substance. So let's just be specific here. Let's talk about water. So the enthalpy of water, enthalpy of anything is equal to little u plus pressure times volume. And so the units, again, are in kilojoules per kilogram because it's per unit mass. And so this represents here, again, just this is enthalpy, spelled this way. This you should be a little bit familiar with since we talked about it in the previous chapter. This is internal energy. And this P is our pressure that we are familiar with, and V our volume. And so what this is basically saying is the quantity of energy of the substance is the internal energy, which is the molecular energy associated with typically it's temperature related, plus pressure times volume. So there is an internal energy component. There's also, depending on the pressure and the volume component, and that'll give us the whole quantity of energy of that substance. If we looked at capital H, this is now where it's just the total enthalpy. Capital H is capital U plus pressure times volume. So this here would just be written in kilojoules, and this is total, represents total enthalpy. That would be this component here. Capital U is total and internal energy. But we specifically like for the property tables, they're all going to be per unit mass, because that way you can use them universally for any mass system. You don't have to know the mass ahead of time, and they're applicable to pretty much any system. You just provide the mass. And so another thing that we're going to be talking about is, let's see, let me just write. So this is what we call little v, and this is specific volume. So specific volume, and that little v is actually equal to 1 over the density. So therefore the units of density are kilograms per meter cubed, so the units of 1 over density are meters cubed per kilogram. And so you'll have we'll have little subscripts to designate what kind of specific volume. So little f represents specific volume. So it's a specific volume. We're going to say of the saturated liquid. Of the saturated liquid. And then V sub G represents specific volume, and now of the saturated vapor. So these are our subscripts. F represents liquid and G represents vapor. To help me understand, to remember, F, I think of that as a fluid. And when I think of fluid, I don't typically think gas. If this confuses you, then don't do it the way I do it. But I think of fluid, I think of like a fluid, which to me a fluid is a liquid. When I think about you should always drink your fluids or keep hydrated, drink a lot of fluids, I don't consider that drinking gas. Right? I always think about it as a liquid. And then G is easier. It represents a vapor, but it's a gas. This one's easier to remember because it's already G. And so AKA vapor, because a vapor is a gas. And fluid, AKA liquid. Though again, I'll have some other professors criticize me because a fluid can also be, a fluid is any system that moves, so it technically could be gas as well. But when I think of drink your fluids, I think of liquid. And when I think of G, so that's F, and I think of G, I think of gas or a vapor. Okay, let's go ahead and create a new sheet here. All right, let me get this a little darker. All right, we talked about phase change. We talked about latent heat is. If I can just spell it right. I did have it right, sorry. Latent heat. So latent heat is the amount of energy absorbed or released during a phase change process. So it has to do with phase change. So it's amount of energy again during the phase change process. So I'm just going to say phase change. So it has to do with the energy that's either released or absorbed during phase change. So if we are talking about, and we're going to say latent heat of vaporization, latent heat of vaporization is equal to amount of heat that's associated with vaporizing liquid. So a common symbol for that is to use lambda like that, and then this would be a V. We don't really use that in our tables. What we typically do is we leave that as an enthalpy, which is it's related to an enthalpy. And more specifically, we actually call it, so it's enthalpy, and we don't have a subscript V. We actually use those F's and G's. So I'll explain why we do this, but that would be associated with F and G together, because it's the energy associated with vaporizing, going from liquid to a gas. And so we would use this symbol here. And then there's also a latent heat of, we don't call it solidification, but that's going from a liquid to a solid. We call it fusion. Latent heat of fusion. We don't use this that much here in this class. But let's go ahead and give you a value here for water. For water, this is for, so I'm going to say water at room temperature. So RT stands for room temperature. So that's anything within kind of the comfort area. We're talking anywhere between 20 and 30 degrees Celsius. And between 1 and 2 atmospheres of pressure. It's typical to see latent heat of fusion about 2200 kilojoules per kilogram. Okay, so I put, so I don't know how to spell here. Let me, all right, so this is kilojoules per kilogram. Kilojoules per kilogram. And for latent heat of fusion, we're just going to say it's lambda. For now, we're just going to say latent heat of fusion. And I'm going to skip the symbol there because we don't really use it in this class. But this is about 330 kilojoules per kilogram. So to get a feel for this, the latent heat of fusion is about 7 to 8 times larger than the latent heat of fusion. Latent heat of vaporization is about 7 to 8 times larger than the latent heat of fusion. And so that means that when we vaporize something, it actually uses 7 to 8 times more heat than when we freeze something. And when we freeze something, that absorbs energy. And so to get a good feel for this understanding, 2200 is fairly large for a substance. That's what makes water such a good thermal transport fluid. This is a very large amount of material. About heat. A kilogram typically of water is about a liter. So a liter can produce 2.2 megajoules of heat if we basically take it from liquid to vapor. That is a really large amount of heat. And that's why we use heat steam or water steam was very popular for steam engines when they were first created. Okay, now another thing I want to explain when we start talking about tables. So going off to a different subject here. You're going to have to focus or brush up on your interpolations. And what interpolation means is, suppose you have two properties here you're looking at. Oh, sorry about that. Maybe I drank too much coffee. It's not much better, but let's say it's temperature in degrees C that you're looking on this left-hand column. And on the right-hand column, let's just say it's V sub G, or specific volume of the gas. And so let's suppose you have 85 degrees, and then you have 90 and 95. So those are the table entries, and you have values for each one of these. 2.8, and then you have for this one 2.3 or 2.4, and then for this last one you got 1.98. Let's go with two significant figures here. So suppose you wanted to you don't want 90, 95. You want to get the specific volume of gas for a temperature of 93. So you wouldn't be able to use this table without interpolating. You need to get a value here, and you would do a linear interpolation between. So your value would be between 1.98 and 2.40. And so I'm not going to go too in depth on interpolation here, but you would go ahead and you would set up, in order to get that, you would set up kind of a similarity triangle, where you would say, well, okay, I have an X and a Y axis. I'm going to say my Y axis, so this is 90 degrees, and I need to find a value at 93, and then just say this is 95. All right, so these are our Y axis, and on our X axis, I'm going to say, well, at 90, we know that this was 1.98, and we don't know what it is here. This is what we're trying to find. We're going to call this X, and at 95, it was 1.98 represents 95. Yeah, I'm even going off of this grid here. 93 is here. 90 represents this one here. And so 90 represents 2.4. Again, 90 is coupled to 2.4. 95 is coupled to 1.98. Sorry for the confusion here. I don't know why I drew this dotted line. And there's a point there that's 93. We don't know what it is. We're going to call that x. So then what we have to do is basically do a similarity triangle assessment here and say the large span of this triangle here is 95 minus 90. The ratio of that, again, that's a 90 here, to the ratio of that to this triangle here. Let me go ahead and change the color here so we're talking. So there's a large triangle here and there's a smaller triangle in here. That's too light. This is similar triangles, right? So the height of the pink triangle is 95 minus 90. The height of the little triangle, so the ratio of the height of the pink triangle to the height of the little triangle, the height of the little triangle is 93 minus 90, is equal to and now we look at the base. So the base of the large triangle is it's 2.4 minus 1.98. Let's see if that'll fit here. 2.4 2.4 minus 1.98, and then that's the base. That's basically this base of this large triangle, and the base of the small triangle, which is here, is equal to 2.4 minus x, or x, I'm sorry, x minus 1.98. So you solve for x. So you get this equation here and has x in it. You just solve for x and that'll give you your value for x. For basically, you'll get the value here for what's the specific volume of gas for at 93 degrees Celsius.